Hi, and welcome back to the Engineering Street. In today's episode, we talk about the Starlink, which is engineered by SpaceX.
SpaceX is developing a low-latency broadband internet system to meet the needs of consumers across the globe. Once it becomes fully operational, Starlink will be able to offer internet access from virtually anywhere on the planet. Therefore, it's suited for areas of the globe where connectivity has typically been a challenge. Unbounded by traditional ground infrastructure, Starlink can deliver high-speed broadband internet to locations where access has typically been unreliable or completely unavailable. The goal is to launch thousands of small satellites, all of which will be in low Earth orbit. They will then be able to transmit fast
They promise low latency and high broadband, but what does that mean? Latency is the time it takes to send data from one point to the next. When satellites are far from Earth, latency is high, resulting in poor performance for activities like video calls and online gaming. Starlink satellites are over 60 times closer to Earth than traditional satellites, resulting in lower latency and the ability to support services which are not possible with traditional satellite internet. This means there is significantly less lag.
On Monday, February 15th at 10:59 p.m., SpaceX launched 60 Starlink satellites from Space Launch Complex 40. This was the sixth launch of the Falcon 9 booster, which previously supported Dragon's 19th and 20th cargo resupply missions to the International Space Station, SATCOM 1B, NREL 108, and a Starlink mission.
We are currently in the beta stage of the Starlink. During beta, users can expect to see data speeds vary from 50 megabytes per second to 150 megabytes per second, and latency from 20 milliseconds to 40 milliseconds in most locations over the next several months as we enhance the Starlink system. There will also be brief periods of no connectivity at all as they launch more satellites, install more ground stations, and improve their networking software. Data speed, latency, and uptime will improve dramatically.
However, there has been concerns about preserving the night sky. Therefore, Starlink teams have worked closely with leading astronomers around the world to better understand the specifics of observations and engineering changes that they can make to reduce satellite brightness.
Goals include making the satellites generally invisible to the naked eye within a week of launch. They're doing this by changing the way the satellites fly to their operational altitude so that they fly with the satellite knife edge to the sun. They are working on implementing this as soon as possible for all satellites since it is a software change. Secondly, they are minimizing Starlink's impact on astronomy by darkening satellites so that they do not saturate observatory detectors. They're accomplishing this by adding a deployable visor to the satellite to block sunlight from hitting the brightest parts of the spacecraft. The first unit is flying on the next launch, and by Flight 9 in June, all future Starlink satellites will have sun visors. To better explain the details of brightness mitigation efforts, we need to explain more about how the Starlink satellites work. Starting with its orbit, Starlink has three phases of flight. The first stage is orbit raise. The second stage is parking orbit, which is 380 kilometers above Earth. And the third is on station, which is 550 kilometers above Earth. During orbit, the satellites will use their thrusters to raise altitude over the course of a few weeks.
Some of the satellites go directly to the station, while others pause in parking orbit to allow the satellites to preset to different orbital planes. Once satellites are on station, they reconfigure so the antennas face Earth, and the solar array goes vertical so that it can track the sun to maximize power generation. As a result of this maneuver, the satellites become much darker because the solar array visibility from the ground is greatly reduced.
Currently, about half of the over 400 satellites are on station, and the other half are orbit raising or in the parking orbit. Satellites spend a small fraction of their lives orbit raising or parking and spend the vast majority of their lives on station. It's important to note that at any given time, only about several hundred satellites will be orbiting raising or parking. The rest of the satellites will be in the operational orbit on station.
Now onto the Starlink satellite itself. The Starlink satellite design was driven by the fact that they fly at a very low altitude compared to other communication satellites. This prioritizes space traffic safety and minimizes the latency of the signal between the satellite and the users who are getting internet service from it. Because of the low altitude, drag is a major factor in the design.
During orbit raise, the satellites must minimize their cross-sectional area relative to the wind, otherwise drag will cause them to fall out of orbit. High drag means that flying the satellites is tricky, but it also means that any satellites that are experiencing problems will deorbit quickly and safely burn up in the atmosphere. This reduces the amount of orbital debris or space junk in orbit.
Resting flight configuration resembles an open book, where the solar array is laid out flat in front of the vehicle. When Starlink satellites are in orbit raising, they roll to a limited extent, about the velocity vector for power generation, always keeping the cross-sectional velocity area minimized while keeping the antennas facing Earth enough to stay in contact with the ground stations.
When satellites reach their operational orbit of 550 kilometers, drag is still a factor, so any inoperable satellite will quickly decay. But the altitude control system is able to overcome this drag with the solar array raised above the satellite in a vertical orientation that we call shark fin. This is the orientation in which the satellite spends the majority of its operational life.
However, the satellites are visible from the ground at sunrise or sunset. This happens because the satellites are illuminated by the sun, but people or telescopes on the ground are in the dark. These conditions only happen for a fraction of Starlink's 90-minute orbit. The diagram highlights why satellites in orbit rays are so much brighter than satellites that are on station during orbit rays when the solar array is in the open book. Sunlight can reflect off both the solar array and the body of the satellite and hit the ground. Once on station, only certain parts of the chassis can reflect light on the ground.
Now on to the physics of the satellite brightness. The apparent magnitude of an object is a measure of the brightness of a star or object observed from Earth. It is a reverse logarithmic scale, so the higher numbers correspond to dimmer objects. A star of magnitude 3 is approximately 2.5 times brighter than a star of magnitude 4. Based on observations that have been taken, current Starlink satellites have an average apparent magnitude of 5.5 when on station and brighter during orbit phase. Objects up to about magnitude 6.5 to 7 are visible to the naked eye. Naked eye visibility is closer to 4 in most suburbs, and the goal for Starlink satellite is for magnitude to be 7 or better for almost all phases of their mission.
There are two types of reflections off of Starlink satellites. diffuse, and specular. Diffuse reflections occur when light is scattered in many directions. Imagine shining a flashlight at a white wall. Specular reflections happen when light is reflected in a particular direction. For example, the glint of sunlight off of a mirror. Diffuse reflections are the biggest contributor to observed brightness on the ground because diffuse reflections go in all directions. You can see diffuse reflections as long as a satellite is visible. This is why Starlink satellites can create the string of pearls effect in the night sky.
Intuitive, but the shiny components of the Starlink satellites are a much smaller problem. Whether diffuse or specular, having a high reflectance helps the satellite stay cool in space. When sunlight hits a specular surface of the spacecraft and reflects, the vast majority of light reflects in the specular mirror reflection direction, which is generally out toward space, not toward Earth. Occasionally, when it does, the glint only lasts for a second or less. In fact, specular surfaces tend to be the dimmest part of the satellite, unless you are at just the right.
The biggest contributors to Starlink being bright are the white diffuse phased array antennas on the bottom of the satellite, the white diffuse parabolic antennas on the sides, and the white diffuse backside of the solar array. These surfaces are all white to keep temperatures down so components don't overheat.
The key to making Starlink darker is to prevent sunlight from illuminating these white surfaces and scattering via reflection towards observers on the ground. While in orbit, rays and the parking orbit, the solar array dominates due to the much larger surface area. However, once the satellites are at their optimal altitude, the antennas dominate because the bright backside of the solar array is shadowed.
So how would they fix it? They've taken an experimental and iterative approach to reducing the brightness of the Starlink satellites. Orbital brightness is an extremely difficult problem to tackle analytically, so they both ground and on-orbit test them. For example, earlier this year, the DarkSat was launched, which is an experimental satellite where they've darkened the phased array and parabolic antennas to tackle on-station brightness. This reduced the brightness of the satellite by about 55%.
This is nearly enough of a brightness reduction to make the satellite invisible to the naked eye while on station. However, black surfaces in space get hot and reflect some light, including in the IR spectrum. So, a sun visor solution will be able to combat that in the future. This avoids thermal issues due to black paint and is expected to be darker than DarkSat since it will block all light from reaching the white diffuse antennas.
However, since the visor is intended to help with brightness while on station, it doesn't shade the back of the solar array, which means it won't prevent orbit rays and parking orbit brightness. For this, they're working on changing the way the satellite flies up from insertion to parking orbit and to station.
They are currently testing rolling the satellite so that the vector of the sun is in plane with the satellite body, i.e., so that the satellite is knife-edge to the sun. This would reduce the light reflected onto Earth by reducing the surface area that receives light. This is possible when orbit raising and parking in the precession orbit because they don't have to constrain the antennas to be nadir facing to provide coverage to internet users.
However, there are a couple of nuisance reasons why this is tricky to implement. First, rolling the solar array away from the sun reduces the amount of power available to the satellite. Second, because the antennas will sometimes be rolled away from the ground, contact time with the satellite will be reduced. Third, the Star Tracker cameras are located on the sides of the chassis, the only place they can go and have adequate field of the view.
Rolling knife edge to the sun can point one star tracker directly at the Earth and the other directly at the sun, which would cause the satellite to have degraded altitude knowledge. There will be a small percentage of instances when the satellite cannot roll all the way to true knife edge to the sun due to one of the aforementioned constraints. This could result in the occasional set of Starlink satellites in orbit rays of flight that are temporarily visible for one part of an orbit.
Moving on to on-station brightness. Satellites spend most of their lives on station, where they will always be in the sharpened configuration during visible passes. They can adjust the solar array positioning in this configuration to reflect light from its largely specular solar cells away from the Earth, and to partially hide it behind the chassis. The main remaining goal is to block the phased arrays and the antennae from the direct view of the sun. The goal is to cover the white phased array antennas and the parabolic antennas on the sides of the satellite.
Using their low orbital altitude and flat satellite geometry to their advantage, they designed an RF transport deployable visor for the satellite that blocks the light from reaching most of the satellite body and all of the diffuse parts on the main body. This visor lays flat on the chassis during launch and deploys during satellite separation from Falcon 9. The visor prevents light from reflecting off the diffuse antennas by blocking the light from reaching the antennas altogether.
Not only does this approach avoid the thermal impact from the surface darkening of the antennas, but it should also have a larger impact on the brightness reduction. As previously noted, the first VisorSat prototype will launch in May, and they will have these black specular visors on all satellites by June. The parabolic antennas on the sides of the Starlink satellites also have visor-like coverings that darken them.
They've been working with leading astronomical groups in this effort to better understand the methods and instruments employed by the astronomy community. While community understanding is critical to this problem, engineering problems are difficult to solve without specifics. The Vera Rubin team has provided a target brightness reduction to guide engineering efforts to iterate on brightness solutions.
Vera Rubin has been described as a limiting case for Starlink due to its enormous aperture and wide field of view. These two characteristics work in concert to produce the perfect storm for satellite observation. Most astronomical systems look at an extremely small section of the sky, less than 1 degree, which makes it exceedingly unlikely that a satellite will cross in front of the imaging system in a given observation.
On the other hand, systems with very large fields of view normally aren't extremely sensitive, meaning that, while streaks will occur, they will have a small impact on the overall data collection. So what can we do to mitigate our impact on these edge cases of wide, fast survey telescopes? Minimizing the impact on astronomy. The huge collecting area of larger telescopes like Vera C. Rubin Observatory leads to a sensitivity test that will render even the darkest satellites visible. They are so sensitive that it won't be possible to build a satellite that will not produce streaks in a typical long integration. There is much that can be done to reduce the impact of satellite streaks, and that starts with an understanding of how astronomical sensors work.
Optical systems use mirrors or lenses to focus light onto an imaging sensor. Most optical astronomy instruments use sensors called charge-coupled devices as the detectors because astronomical targets such as distant supernovae and galaxies, are generally dim at the limit of what can be detected by a sensor. For these applications, the lower noise levels of CCDs allows for higher signal-to-noise ratio for a given image, making it easier to see very faint features in the universe.
CCDs suffer from a key drawback. When compared to other common sensors, like the CMOS sensor in your iPhone, if you point your cell phone at a bright light, you'll see all the pixels saturate and turn white in the region of the bright source. If you look at the same target with an optical system that uses a CCD sensor, you'll notice that this bright spot extends to create vertical stripes on the image.
This difference is due to the way each sensor type reads the value for each pixel. While a CMOS sensor essentially has an amplifier at each pixel that turns the light collected into a digital value, a CCD sensor has a limited number of amplifiers and moves that collect light in the form of electrons across the sensor to be digitized. This mechanism means that saturated pixel on a CCD tends to wipe out data from an entire column of pixels.
This effect, commonly referred to as blooming, is one example of a very small but bright source of light can impact an astronomical observation. This principle is the core of our mitigation efforts. While it will not be possible to create satellites that are invisible to the most advanced optical equipment on Earth, by reducing the brightness of the satellites, we can make the existing strategies for dealing with similar issues, such as frame stacking, dramatically more effective. SpaceX is committed to making future satellite designs as dark as possible. The next generation satellite, designed to take advantage of Starship's unique launch capabilities, will be specifically designed to minimize brightness, while also increasing the number of consumers that it can serve with high-speed internet access. While SpaceX is the first large constellation manufacturer and operator to address satellite brightness, they won't be the last. As launch costs continue to drop, more constellations will emerge, and they too will need to ensure that the optical properties of their satellites don't create problems for observers on the ground. Thank you for watching today's episode of the Starlink. Comment down below your thoughts on the Starlink. Don't forget to like, share and subscribe. And as always, see you soon on the engineering